Graphene is a single layer of graphite, which is a planar monoatomic layer of carbon bonded in honeycomb lattice. So each carbon atom has free electrons in covalent bond and has one free electron, so that makes graphene very excellent conductor. Graphene has some wonder properties that makes it versatile material. For example, it's between 200 times stronger than steel, and it's the best electric and also best heat conductor, and it's almost transparent. And there are many applications of graphene in the field of electromagnetics and photonics. For example, it can be used for guiding electromagnetic surfaces and transportation optical modulator, optical polarizer, and tunable infrared devices. But the question is, now we will see what is the model of electromagnetic model of graphene. In the field of the physical thickness of graphene is extremely fine. I mean, it's just the thickness of the graphene is one carbon atom dimension, which is around 0.1 nanometer. So it can be fairly modeled as a zero thickness surface, two-sided surface in the problems, and characterized by surface conductivity. The surface conductivity of graphene consists of two terms, intraband term and interband term. The intraband term, term of conductivity has loop-like expression. In terms of frequency, has loop-like expression, and the interband term has complex expression, which involves logarithm function. As you can see, the conductivity of graphene is a function of frequency, chemical potential, scattering rate, and temperature. But in electromagnetic simulation, we accept frequency, we set all the parameters constant, and the only parameter is frequency. So, in this figure, you see the real part and imaginary part of conductivity of graphene. In this part, in this region, the interband conductivity, terms of conductivity is dominant term, and from this point, the interband conductivity gets more important. As you can, if you consider the curve equation for the magnetic field, we see that the imaginary part of conductivity looks like the permittivity. I mean, conductivity has two parts, real parts and imaginary part. The real part is lost, and the imaginary part acts like conductivity. So, in this region, we have very low loss because the real part of graphene, real part of conductivity is almost zero, and we have negative values of imaginary part. So, in this region, graphene can be modeled as a thin dielectric slab with negative permittivity. This is the basic idea behind the works by Vahid and Enveta that graphene used used for transportation optics. And also once again, look at the conductivity of graphene. The conductivity of graphene depends on chemical potential, and chemical potential can be controlled by doping and external electrostatic bias. So we can tune the conductivity with an external bias, and which is shown in this figure. And if for magnetostatic bias graphene, the conductivity gets anisotropic and it can be written in the tensor form as written in this formula. Again, all the elements of tensor is function of frequency, chemical potential, and also magnetostatic bias. This anisotropic properties of graphene causes that graphene can rotate the polarization of electromagnetic waves. And now, an important question: how we can model graphene in electromagnetic simulation? Electromagnetic simulation fairly means computational electromagnetic methods, and we need to model graphene in computational electromagnetic methods. There are two problems for such a purpose. First, the conductivity of graphene is a complex function in terms of frequency. This is a problem when you are working with time domain methods, for example, finite difference time domain, for example, finite integral method in time domain, and other time domain methods. And the other problem is how to model very thin, zero thickness slab or surface in volumetric discretization method. For example, finite element, for example, finite difference. These methods discretize and mesh the volume, and the graphene is a zero thickness surface. So let us first see the first problem. The first one, as we have seen, the conductivity of graphene is a complex. It has complex expression of frequency, and it cannot be directly implemented in a time domain method. But it is not a new problem. We have a similar problem for example, for modeling of biological tissue, or for example, metal in very high frequencies. The similar solution can be applied for this problem. The rational functions can be easily implemented in the time domain methods, rational function of frequency. And so we can approximate the complex conductivity of graphene by sum of rational functions, as we write here. Here, sigma g is the conductivity of graphene, which is approximated by sum of rational functions, and which can be described by some roots and some residues and some poles. Now, curve fitting and vector fitting techniques can be applied for extracting these residues and poles. If we approximate the conductivity of graphene with this expression, we can easily implement it in time domain method. This slide shows the accuracy of this approximation. As you see, for a very wide range of frequency, from 100 gigahertz to 100 terahertz, the conductivity of graphene can be approximated fairly by just only four pairs of residues and poles. Now, the second problem. The second problem is how to model a very thin, zero thickness surface in volumetric method. Actually, the graphene is modeled with zero thickness surfaces. And what characterized by a surface conductivity. But what does surface conductivity mean? The surface conductivity fundamentally means a boundary condition at two sides of the sheet. For example, here you have this boundary condition, which namely conductive sheet or resistive sheet or impedance sheet boundary condition. Now, we need to implement this boundary condition in our method. When you are working with the method discretizing the meshing surface, such as method of moment or boundary element value, is no problem. This is no matter. You can easily implement the boundary condition and model it in this method. For example, some faculty and carrier have done some work, some simulation using method of moments. But method of moments and boundary element values, boundary element method are in most problems are significantly less efficient than volume discretization methods such as finite difference, finite element, and finite volume methods. So we need to model graphene in volume discretization method. But it is not a straightforward job, because as we see, for example, in this figure, the placement of field components in this cell is not compatible with boundary condition with conductive sheet boundary condition. So what should we do? There are two solutions for this problem. First, implementing or modeling graphene as a very thin volumetric group. We can, the easiest way is to consider graphene as a very thin volumetric layer with assumed thickness of delta. And then converting the surface conductivity of graphene to volumetric conductivity by dividing it to the assumed thickness. But the conductivity of graphene is in play. If you convert it to volumetric conductivity, volumetric conductivity has both in-plane and out-of-plane conductivity components. So it is better to convert the surface conductivity to volumetric conductivity and set the out-plane conductivity to 0. And if we apply external magnetic bias, then the non-diagonal elements of matrix appear. So the advantage of this, volumetric implementation is that it is very easy and compatible with all numerical methods and can be easily used in all commercial software. But the disadvantage of this technique is that you need very fine mesh because the thickness of the graphene needs to be very fine to have accurate results, and it makes the simulation very time consuming. Here you see the convergence of results as a function of graphene thickness approaching the graphene thickness to 0. The convergence, the results approach to the exact solution obtained by method of moments. And here you see another curves. Usually the thickness of volumetric layer is set to 0.325 nanometer in the simulations to have accurate results depending on the problem you are solving. But is it possible to directly model boundary condition in the volume discretization methods such as finite difference time domain? Let's see in the literature. The only work we found is the work by Wu and Han in 1992. But the method presented in this work is unstable and is reported by further papers. We implement the conductive sheet boundary condition in the finite difference time domain last year. Here you see a one-dimensional finite difference time domain study. And if we put a conductive sheet here, we need to define the magnetic fields at both sides of the sheet. And then consider Maxwell's curl equation for E and and discretizing the equation by backward and forward difference scheme, you have a couple of equations for left side and right side. Here we need the electric field at the sheet, but it is not defined in the E cell. But it can. This component can be substituted by conductive sheet boundary condition, like as here. And substituting this equation to these equations, you can derive an operating equation for these two components. And the problem were solved. Similar procedure can be applied for 3D cells, and we have done it in publishing in our papers in transaction and conduct variation. And recently, Feliciani have done it with finite element method. He first extracted the equivalent circuit for conductive sheet boundary condition, and then implement the model the equivalent circuit in the finite element method. Here you see the results of this problem using both finite difference and finite element method, which are in very good algorithm. So, the advantage of this method is that, the advantage of modeling direct implementation of boundary condition in the finite difference. In the volume discretization method is that you can choose the mesh size independently. But the disadvantage is that you need to modify the method to be compatible with actually boundary conditions. So let's see the space of commercial EM solver. First, FECO. The FECO has the solver has a method of moment frequency domain solver. Because of the feature of the method of moment, the graphene sheet can be modeled in FECO as a zero thickness sheet, but there is no inverse of the surface conductivity as in a lookup table. And then here, you can create in a FECO, you can create an impedance sheet and the real part and imaginary part of surface conductivity in a lookup table in terms of frequency. In CS, the main solver of CST is finite integral method both in frequency and time domain. And there are two ways for modeling graphene in CS. The first, volumetric implementation, and the second is surface impedance or surface resistive sheet implementation, which is possible in CSC 2013 or later. In CSC, you can, when you are working with time domain solver, you can either approximate the conductivity by yourself, or let the software approximate the conductivity. Here you can insert, you can extract the pores and residues by yourself and insert it to the software. And here you can give the conductivity of the sheet as a function, as in terms of frequency in a lookup table. And the software approximated by some of fractions. And CST seems to be capable to model magnetic-statically biased graphene sheet because it is possible to define full analytic tensor in the CST macro study. And you can also define. You can also give model graphene in CST using surface impedances and give the resistivity, surface resistivity, and surface real part and imaginary part of surface resistivity as a function of frequency in a lookup table in software and software scalability. In CSBC 2014, we have embodied model for graphene in the software, and it's just need to put the chemical potential and temperature of the graphene to the software, and the software does everything. And the other software is numerical. The numerical is most common software package used for simulation of graphene because the phase difference time domain is the best option to choose when you are working with high frequency terahertz and macro regime and optical regime. The graphene can be modeled in numerical using just with the volumetric light as a volumetric light, and the thickness of the layer should be in order of 0.3 or 2 nanometers. 2 nanometers. And the numerical has embodied model for graphene in its database, as you see here, which parameter is 169 is defined as a parameter of graphene. Thank you for your attention.